today's session. As you know, this is our last second class before the course is going to complete. It was a short course, as I mentioned earlier, also. I really hope that every one of you are up to date with the lectures which are being published. So, I guess week 4 lectures are already there, and this is the week 3rd which we want to discuss today. Okay. So, if you have gone through the lectures, what Professor Manik Das has discussed in this particular week are few different types of cells, and finally we dwell into the biological aspect of bioelectrochemistry. Okay, so in the first week and second week, it was more towards chemistry and electric part of the bioelectrochemistry. But by the third week, finally, when we are entering, we started to um, see the bio part, which is the bioelectricity. Okay, so continuing with the discussions which were there in this particular week, I would like to brief you guys about the cell membrane, right? Because the moment we talk about bioelectrochemistry, the electrical part, the chemistry part, and the biology part, it all begins with a cell. Okay, at the end of the day, is the cell which is maintaining a particular potential difference, because of which the electricity and the flow of electrons is there, and all the chemical processes which are taking place, they're all interlinked. Okay, so once we start with the cell membrane, so what exactly is the cell membrane? The basic definition of the cell membrane or plasma membrane is: the plasma membrane or the cell membrane provides protection for a cell. It also provides a fixed environment inside the cell, and that membrane has several different functions. One is to transport nutrients into the cell and also to transport toxic substances out of the cell. So this is pretty straightforward definition, right? So it's just the protective boundary around a cell which delineates the cell's internal environment to that of the external environment. Okay, and this uh, distinction between one cell to another cell helps in having different organs and different types of tissues inside single organism. Okay, so every cell has same components, similar DNA, and everything is same, but still all of our tissues are not identical or not same, right? So there are slight changes, there are differences from one tissue to another tissue. So how come this differences arise in the cell? So the to understand this, we should know what exactly is a cell. So the moment I say the word cell, or imagine, our imagination goes towards circular thing and something inside. Okay, so what is that circle? The boundary or the periphery, the circle which you are drawing in your imagination the moment I am telling you guys the term cell, is the cell membrane. This confides the cell material inside it. So here, this is the representation of a cell membrane. This is a small patch of the cell membrane. So though cell membrane might look like very small and very non-functionally, right, but it is one of the most functionally diverse component of a cell, right? So the cell membrane of living organisms, so preferably we'll talk about eukaryotes, right? So higher organisms is made up of majorly two parts: the lipidic part and the protein part. The lipids are generally, there are different types of lipids. Okay, one type of lipid which is predominantly present in eukaryotic cells is called phospholipid. Okay, this phospholipid makes the bilayer type of membrane. In this, multiple proteins are present. They can be of different types, as you can clearly see here. So if we start from left to right, this is a type of protein which is crossing both of the bilayers, right? This type of proteins are called integral proteins or transmembrane proteins, because they are transversing whole of the membrane. This particular type of protein which is embedded in the membrane but not exactly crossing the whole membrane are called integral type of protein or peripheral or peripheral type of proteins. Okay, then just give me 1 minute. I guess I changed some settings here. Okay, I don't think so it's there. Let me check. Okay, okay, yeah, this won't be a problem now. So this membrane, as I mentioned, this bilayer is made up of lipids. Majorly phospholipid type of lipids are present. Then we have different types of protein. One type of protein which transverses both of the lipid bilayers or the membrane is called transmembrane proteins. Others which are present only in one side or one leaflet of a protein of this bilayer is called peripheral proteins, right, as you can see here. Then some of the proteins which are facing the extracellular side have glycoproteins associated with them, right? Then these are again integral membrane proteins or transmembrane proteins. Then some surface proteins are there which are not at all embedded in the membrane but are just associated with the membranes, right? Then we have these proteins. These are again type of integral membrane protein, but they have predominantly alpha helices in their structure, and hence they are called alpha helix proteins. They're still type of integral protein, as you can see here, right? So as the lipids are there, one of the characteristic of lipid of this particular lipid molecule is this. If you see all these red dots, red circles, these are called polar head groups. Okay, so polar means they'll be loving water, so they'll face always towards outside of the cell wherever there is water. So this side is extracellular, which is water, aqueous medium, right? And this side, the integral of a cell, is also aqueous, right? Hence you'll see these polar heads facing the aqueous environment. And the middle environment of this membrane is the chains of these lipids, right? These chains are hydrophobic in nature. Hence, water cannot pass through this membrane directly. Correct? So these are called hydrophilic heads. These red ones and these yellow are called hydrophobic tails because they do not like water and hence won't allow any water soluble substance to cross through them. Okay? This is the basic of cell membrane. Let us go to uh, okay, I guess, let's go to the brief description of the cell membrane and see what it exactly means.
I knew I was underwater.
Just give me 1 minute. Yeah.
Video, we will talk about cell membrane. The cell membrane is also called the plasma membrane, or plasmalemma. It makes the outer protective wall of the cell. It maintains the shape and size of the cell. And obviously, any exchange between the inside and outside of the cell happens through the cell membrane only. Now let's talk about its structure. It's very thin and pliable. Its thickness is only about 10 nanometers. The main constituents of the cell membrane are lipids, proteins, and carbohydrates. Lipids make up about 40%, proteins about 55%, and carbohydrates about 5% of the membrane. Now let's talk about each of these components one by one. First, the lipids. The lipids are arranged in two layers, like a sandwich.
As you can see in the image also, as we discussed just before coming to this video, there are different types of lipids, right? But in plasma membrane, a phospholipid type of lipid is predominantly present in eukaryotes, okay? Which is represented like a head and two tails.
Thus they make a lipid bilayer. It mainly has two types of lipids, phospholipids and cholesterol. Along with them, there are other types of lipids as well. Phospholipids are by far the most abundant among them. This is a phospholipid molecule. It has a phosphate head, which is hygrophilic. Means it likes to be with water. And a lipid tail, which is hydrophobic. This means it likes to stay away from water. So the phospholipid molecules arrange themselves in this type of bilayer form, where phosphate groups are on the surface in contact with water, and lipid groups are on the inside, away from water. This is called hydrophobic interaction. An interesting thing about this is that in this arrangement, the phospholipid molecules do not make any strong bonds with each other. These molecules are actually freely moving along the plane of the layer. Thus, the membrane is actually in a liquid state, not the solid one. This is called the fluid mosaic model of the membrane. Now, let's continue with the next lipid, cholesterol. Cholesterol molecules are dissolved in the lipid bilayer. It controls the fluidity of the membrane. At a modest concentration, it decreases the fluidity. Or in simple words, it makes the membrane more rigid. And at high concentrations, it increases the fluidity of the membrane. So these were the lipids. Talking about the permeability of the lipid bilayer, it's semi-permeable. As it's made up of lipids, other lipids and lipid-soluble substances can dissolve in it and thus pass through it.
Yeah, because the interior of the membrane is liquid, is like the whole membrane is in liquid state, but this internal part is lipidic, which hates water, right? So hydrophobic. So all the compounds and the substances which are hydrophobic or say lipid soluble will be able to pass through this membrane, but not the ones which are hydrophilic or water loving, because they'll face a huge energy barrier or repulsion when they reach this center of the membrane. Okay.
Water and water-soluble substances, as well as large molecules, cannot pass through it. The lipid bilayer makes the backbone of the membrane, to which the proteins and carbohydrates are attached. And that brings us to the protein component of the cell membrane. Proteins are mostly in the form of glycoproteins. Broadly, they are categorized into two types: integral membrane proteins and peripheral membrane proteins. Integral membrane proteins are tightly integrated with the lipid bilayer. And peripheral membrane proteins are loosely attached to lipids, or integral membrane proteins. The membrane proteins serve as transport proteins to allow passage of water and water-soluble substance, receptors to receive signals, as second messengers in intracellular signaling, as enzymes, as adhesion molecules to attach the cell to extracellular matrix or make cell-to-cell contact, form a submembrane cytoskeleton that provides strength and resilience to the membrane, and finally, they may be expressed as antigens.
So these are the basic functions which the membrane proteins perform. So first function is the transport proteins. Like these proteins, they help in pure transportation of substances from outside to inside or vice versa. Because we know only the lipid soluble molecules can pass through it, but there are still many components which we need to transport inside the cell, right? The food which we are eating, they have different components, so it needs to be transported inside, and all the byproducts which are there or toxic to the cell, it needs to be excreted outside the cell. Okay, so that work is done by the transport proteins of the membrane. Second, receptor. So receptor molecules are the ones which receives some signal, so that the cell knows what is going on from the outside environment and what it needs to do to adapt to the changing environment or the stimuli which is coming. Then intracellular signaling. So there are certain molecules which will dissociate themselves from the membrane and act as a messenger molecule, which again will tell the cell to either start some function or stop some function. Then enzymes, obviously they're gonna catalyze some reactions. Adhesion molecules. So one cell is there and the extracellular material is there. If there is no anchoring of the cell to that matrix or to that material, the cell will float, right? But it needs to be stationary at some place so that it has a strong solid mass like structure, right? So those are done by the membrane proteins which function as an adhesion molecules. Then antigens. So at the end of the day, so you know cancers and other diseases in which the macrophages actually need to identify the faulty cell. So for example, for some reason this particular cell is not functioning well, so the system should know that this cell needs to be eliminated from the system, right? So there are proteins which express themselves as antigen and which will be like detected by the other cells of our system and will be and their fate will be decided. Okay.
So these were proteins. Now let's see the last component of the cell membrane, carbohydrates. Most of the carbohydrates on the cell membrane are in combination with proteins and lipids in the form of glycoproteins and glycolipids. The carbohydrate portion in these molecules is usually dangling on the outer side of the cell. Along with these are also other carbohydrates attached loosely to the outer surface of the cell. All these carbohydrates cover almost the entire outer surface of the cell. This carbohydrate coating of the cell is called glycocalyx. Functions of the carbohydrates are as follows. Most carbohydrates have a negative charge. So they make the outer surface of the cell electronegative, which repels other negatively charged objects. Second, neighbor cells may get attached to one another through their glycocalyx. They may serve receptor functions. And finally, they may be involved in immune reactions. So this was all about the cell membrane. Now let's have a quick summary. The cell membrane makes the outer wall of the cell. The central lipid bilayer is made up mainly of phospholipids and cholesterol. It's fluidic in nature and permeable to only lipid and lipid-soluble substances. Attached to the lipid bilayer are proteins that serve as transport proteins, receptors, second messengers, enzymes, adhesion molecules, submembrane cytoskeleton, and antigen. And we also have carbohydrates, making the outer coat, called glycocalyx. The carbohydrates give the cell surface a negative charge, help one cell to attach to the other, serve as receptors, and participate in immune functions. That's it for this video. Click here to read.
Right. So now do you understand what exactly are the functions of a membrane and how important having a cell membrane is? So now why I'm discussing cell membrane in a place where we are talking about bioelectrochemistry, right? Electricity is involved, chemistry is involved, right? So there is a potential difference. So till now we have seen galvanic cells, right? So the basis of galvanic cell is spontaneous chemical reactions. So why we are saying spontaneous chemical reactions? Because there is difference in the potentiality of the substances which are involved, which leads to the flow of electron, right? Meaning there has to be a established potential difference to assure there is electricity or flow of electron, right? So across the membrane we have membrane potential in living organisms. Okay, so membrane potential, also transmembrane potential or membrane voltage, is the difference in electric potential between the interior and the exterior of a biological cell. It equals the interior potential minus the exterior potential. Okay, so the potential will be from inside to outside, it will be measured. This is the energy, that is work per charge, which is required to move a very small positive charge at constant velocity across the cell membrane from the exterior to the interior. So what it says, let's break down the definition. So the potential or transmembrane potential or membrane voltage is equal to the interior potential minus the exterior potential. Okay, this is the energy, that is the work per charge which is required to move a very small positive charge at constant velocity across the cell membrane from the exterior to the interior. If the charge is allowed to change velocity, the change of kinetic energy and production of radiation must be taken into account. Typical values of membrane potential, normally given in units of millivolts and denoted as MV, ranges from -80 to -40 millivolts. For such typical negative membrane potentials, positive work is required to move a positive charge from the interior to the exterior. However, thermal kinetic energy allows ion to overcome the potential difference for a selectively permeable membrane. This permits a net flow against the gradient. Okay, this is just like kind of osmosis. To have better understanding of this, we have two small videos which will explain what exactly a membrane potential is. Okay.
Glow and Lovely.
Just give me 1 minute. I'll skip the ad. Yeah.
Membrane potential, or membrane voltage, refers to the difference of electric charges across a cell membrane. Most cells have a negative transmembrane potential. Because membrane potential is defined relative to the exterior of the cell, the negative sign means the cell has more negative charges on the inside. There are two basic rules governing the movement of ions. They move from higher to lower concentration, just like any other molecules. Being charge-bearing particles, ions also move away from like charges and toward opposite charges. In the case of the cell membrane, there is a third factor that controls ion movement: the permeability of the membrane to different ions. Permeability is achieved by opening or closing passageways for specific ions, called ion channels. Permeability can change when the cell adopts a different physiological state. Consider this example. Two solutions of different concentrations of sodium chloride are separated by a membrane. If the membrane is equally permeable to both sodium and chloride, both ions will diffuse from higher to lower concentration, and the two solutions will eventually have the same concentration. Note that the electric charges remain the same on both sides and membrane potential is zero. Now let's assume that the membrane is permeable only to the positively charged sodium ions, letting them flow down the concentration gradient while blocking the negatively charged chloride ions from crossing to the other side. This would result in one solution becoming increasingly positive and the other increasingly negative. Since opposite charges attract and like charges repel, positive sodium ions are now under influence of two forces. Diffusion force drives them in one direction, while electrostatic force drives them in the opposite direction. The equilibrium is reached when these two forces completely counteract, at which point the net movement of sodium is zero. Note that there is now a difference of electric charge across the membrane. There is also a concentration gradient of sodium. The two gradients are driving sodium in opposite directions with the exact same force. The voltage established at this point is called the equilibrium potential for sodium. It's the voltage required to maintain this particular concentration gradient and can be calculated as a function thereof. A typical resting neuron maintains unequal distributions of different ions across the cell membrane. These gradients are used to calculate their equilibrium potentials. The positive and negative signs represent the direction of membrane potential. Because sodium gradient is directed into the cell, its equilibrium potential must be positive to drive sodium out. Potassium has the reverse concentration gradient, hence negative equilibrium potential. Chloride has the same inward concentration direction as sodium, but because it's a negative charge, it requires a negative environment inside the cell to push it out. The resting membrane potential of a neuron is about negative 70 millivolts. Notice that only chloride has the equilibrium potential near this value. This means chloride is in equilibrium in resting neurons, while sodium and potassium are not. This is because there is an active transport to keep sodium and potassium out of equilibrium. This is carried out by the sodium-potassium pump, which constantly brings potassium in and pumps sodium out of the cell. The resulting resting potential, while costly to maintain, is essential to generation of action potentials when the cell is stimulated.
Okay. me a minute and I just check whether the recording is being on or not.
My silly little heart, it isn't.
Yeah, it's taken care of. Yeah.
Have three different kinds of potentials: resting, graded, and the action potential. First, let's see what happens.
This we are talking about now the action potential, right? And why the action potential? Because it is equivalent to, okay, I have not discussed this with you, but see, we are talking about potential difference. Now we understand why there is potential difference, right? Because of the concentration differences of the ions across the cell membrane. And why that is? Because of the semi-permeable nature of the membrane. Now, what is the use of this difference of ions for generating a membrane potential? So the basic thing which we use here is, so you are able to listen to me, you are able to hear me, right? All this thing is happening because your sensors are there. So your sensors are helping you understand the physical world. But how they are exactly doing? So they do it by the transmission of potential from one end of a neuron to another end, which connects you from the stimuli, say the external environment. It goes to your brain, the information is interpreted there, and then again the signal is sent to you, to the respective organs, or say sense organ of yours, to take appropriate action with respect to it, right? So our nervous system, which is made up of neurons, is dependent upon this functionality of the difference of concentration of ions across the membrane to maintain a potential difference. And how we can use it and how we understand things is completely on the basis of how the action potential is traveled throughout the neuron. So that is why we are focusing on the action potential with the context of neurons. Okay.
Happens at resting potential, which is at minus 70 millivolts. The neuron maintains this potential due to differences in permeability of ions on either side of its cell membrane, as well as the sodium-potassium pump. The ions contributing to the charges on either side of the membrane are negatively charged proteins, negatively charged chloride, positively charged sodium, and positively charged potassium. Now, there are several kinds of channels found in cell membranes, allowing for the transport of substances from one side to the other. Two kinds are important in the context of action potentials: leaky channels and voltage-gated channels. Leaky channels allow the free flow of substances through them. Voltage-gated channels are only open at certain voltages. Back to the ions. Chloride and the proteins stay put, as they don't have a means to cross the membrane. However, the neuron does have leaky sodium and potassium channels. These are always open, and allow some flux of these ions. So what do the ions do? First, there's a lot more potassium in the cell than outside the cell. The potassium wants to rush out of the cell because of the chemical gradient, but wants to stay in the cell because of the electrical gradient. Like charges repel. Similarly, there's a lot more sodium outside the cell than in it, and the sodium has its own electrochemical gradient. Now, if you were to just let the ions do their thing and flow through these leaky channels, eventually, a bunch of sodium would rush in, and we'd lose that potential. However, the sodium-potassium pump is at work. The energy from one ATP hydrolysis reaction allows this pump to transfer 3 sodium ions out and 2 potassiums in. As a result, the neuron maintains its resting potential of minus 70 millivolts. A graded potential is a change in potential that can vary in size, with magnitude depending on the intensity of the stimulus, and occurs when the neurons get excitatory postsynaptic potentials, or EPSPs, or inhibitory postsynaptic potentials, or IPSPs. Dendrites are a neuron's input zone, where a neuron can get EPSPs and IPSPs from other neurons. The neuron cell body is like a calculator, integrating these signals. When the summation of graded potentials results in a potential of minus 55 millivolts at the axon hillock, an action potential occurs. Hence, EPSPs make it more likely that an action potential will occur, while IPSPs make it less likely. Unlike graded potentials, which are changes in potential varying in size, action potentials are all or nothing. More intense stimuli simply mean a higher frequency of firing. So let's go through the steps of an action potential. We start off at resting potential. Voltage-gated sodium and potassium channels are closed. Then, a stimulus causes some voltage-gated sodium channels to open. Once we get to the threshold of minus 55 millivolts, the action potential begins, with lots of other voltage-gated sodium channels opening. With sodium channels open, depolarization occurs. Sodium rapidly rushes into the cell, and the voltage soars up to plus 30 millivolts, at which point the voltage-gated sodium channels close. Potassium channels now open, and repolarization occurs as potassium rapidly rushes out of the cell. The voltage zooms down and overshoots the minus 70 millivolts before the potassium channels can close. Finally, the sodium-potassium pump restores the resting membrane potential. It does a conformational change thanks to an ATP molecule being hydrolyzed. Again, this conformational change results in 3 sodium atoms being shuttled out of the cell, and 2 potassium atoms being shuttled in. We've now seen what happens locally at one segment of the axon, but how does the action potential propagate? Well, when the sodium ions are rushing in during depolarization, they repel each other and so spread out. This makes the next section of the axon reach threshold, and also have an action potential. Why doesn't the action potential travel backwards, though? At the same time as the first section is depolarizing, the section of axon behind it is experiencing repolarization, and the potassium rushing out results in a refractory period. There is an absolute and relative refractory period. During the absolute refractory period, which coincides with most of the action potential's duration, you can't trigger another action potential, because the sodium channels are briefly inactivated. The membrane needs to be hyperpolarized before that can happen. During the relative refractory period, only a very strong stimulus can cause an action potential, since the membrane is below the resting potential and you need a stronger EPSP to get to threshold. Another important point, action potential propagation is slow. That's why most of your neurons have myelin sheaths, which are rich in lipids. Myelin sheaths are made by oligodendrocytes in the central nervous system and Schwann cells in the peripheral nervous system. They insulate the axon and prevent leakage of charged ions. Instead, you get what's called saltatory conduction, in which action potentials only occur in the spaces between the myelin, called nodes of Ranvier. In addition to myelin sheaths, neurons with larger diameters also have faster transmission speeds. Once the action potential reaches the end of the axon, there are terminal buttons there. The depolarization triggers the opening of voltage-gated calcium channels on the presynaptic membrane, and calcium rushes into the terminal button. This causes exocytosis of vesicles full of neurotransmitter molecules, and neurotransmitter is released into the synaptic cleft, where the neurotransmitters attach to the receptors of the postsynaptic neurons, causing EPSPs or IPSPs, and potentially triggering another action potential.
If you like this video, please like and subscribe. It would help me make
So this was just an added information about the action potential, because this is how the biological system works. And with this knowledge and information, we have actually come across a long way where we can make head caps which will help us um, decode these potentials, the energy associated with these potentials, to understand better, and non-invasive processes to understand what is going on in your brain. Okay, so having this information actually comes handy. To elaborate more on the subject, so you can see here, this is just the representation of the membrane here. So as I mentioned, the membrane is bilayer, in which this is the lipid part of the membrane, and there are no proteins shown here. So imagine if there are no proteins and only lipid is there. So this is a hydrophobic part of the cell membrane, right? So what will this allow from it to pass? Okay, so very small hydrophobic molecules such as gaseous molecules don't require any type of transporter or protein to uh, go through the membrane, right? Because these are very small and there is no much hindrance for these molecules, and hence they don't have any resistance which they have to face, and hence they can diffuse easily. If we talk about small uncharged polar molecules, water, urea, and glycerol, some of them which will pass depending upon the size and the electrostatic force, if it is not too much towards the negative direction, it will pass through it. Okay, and via diffusion. But you need to remember the rate of diffusion will be very, very, very slow. Okay, Then we talk about large uncharged polar molecules such as glucose, which is our energy source. It won't be able to pass, so it's impermeable to these molecules and only pass through facilitated diffusion or active transport, which means we need to have proteins for the transportation of large uncharged polar molecules. Then ions such as sodium, potassium, chlorine, calcium, they won't be able to pass because membrane is completely impermeable to these ions. They can only pass through diffusion or active transport. Again, they will require specialized transport proteins which will solely work for the transportation of ions, for the transportation of polar molecules, and for transportation of other solutes which are not membrane soluble. Okay, so this is just a brief summary. Now, building up on the same concept of membrane, why I want to put more effort here is because this is the sole principle, and the how exactly the membrane is maintaining these ions, resulting in the potential difference, help us understand how the transportation and the survival of the cell is happening. Okay, so again, here is the representation. This is the cell membrane, this is the extracellular aqueous medium, this is the intracellular aqueous medium. So you can see there is charge separation because of the selective permeability of the membrane. There are specialized proteins which are there to transport ions because ions are impermeable to the membrane via diffusion. And then there is a difference due to the selective permeability in the concentration. So overall you can see that the inside of a cell membrane or inside of a cell towards the membrane, it is predominantly negative environment, and outside it is predominantly positive environment due to the difference in the ionic concentration. Okay, looking at the numbers, because till now we are just talking about concentration, then what exactly is the concentration difference? So if you talk about sodium, it is the inside of the cell, it is less, right? You can see here the ion concentration is less of sodium inside, but how much less? It's 15 millimolar. Outside of the cell, it is almost 10 times more than the inside concentration, that is 150 millimolar. If we talk about potassium, which is more inside in comparison to the outside, it is again 150 millimolar and 6 millimolar. If we talk about chloride, which is more outside in comparison to the inside of a cell, it is 9 millimolar and 125 millimolar respectively, right? And then we talk about calcium. Calcium is again following the potassium's footprint, so it is more it's following the chloride, so it is less outside, that is 100 millimolar, and less more outside, that is 1.2 millimolar. Okay, this is the basic concentration distribution of ions, important ions across the cell membrane. Now we'll delve into our questions for this. As you know, for bigger questions I will give you guys 1 minute each, but for smaller questions or subjective questions or theoretical type of questions, I'll give you guys 45 seconds to attempt, but every one of you needs to attempt those questions. Okay, let's go ahead and start with our discussions. So the first question says, lithium has a very low standard reduction potential, that is, this is how we represent a cell, right? Lithium ion and lithium coupled, blank, versus standard hydrogen electrode, thus making it suitable for high density, high voltage battery cells. So basically what it is asking is, what is the standard reduction potential of lithium when compared to the standard hydrogen electrode? For this you guys have 1 minute, I'll say, because this is pretty common, but still I want you guys to go into your lectures which you guys have undergone and tell me what is the right answer. So your time starts now. So the correct answer for this question is minus 3.05 volt. This might be easy if you know which sign to use first of all, then you can eliminate two options very clearly. So you know standard hydrogen electrode is for SHE, it's 0, right? So it has to be suitable for high density high voltage, then the voltage associated with the element should be negative, but how much negative, this we need to know. So it's minus 3. This is one of the best element which you can use for the batteries, and you know in the last lectures we have also discussed that a Nobel Prize was also awarded for this. Okay, so the standard reduction potential is in a category known as the standard cell potentials or standard electrode potentials. The standard cell potential is the potential difference between the cathode and anode. For more information, this is just the reference of it. The standard potentials are all measured at 298 Kelvin, 1 atm and with 1 molar solutions. This is the table representing the standard electrode potentials for all the elements which are used, and you can see at the bottom we have lithium. It has the most negative electrode potential, hence it is suitable for making a battery which is high voltage and high power, right? As you can see, if you see here, this is the increasing strength as an oxidizing agent, and this is your standard hydrogen electrode at 0. So this is the reference point. Anything positive will have a strong oxidizing agent property, and anything below this will have strong reducing agent property. So reducing means it will donate electron very quickly in comparison to the standard hydrogen electrode. Hence the spontaneity of the reaction will be more the negative sign, greater the value, more effective it is to initiate the spontaneous process and keep going on. With this, I will see now how exactly standard hydrogen electrode is measured. In the lecture it was discussed earlier, but I want you guys to again go through those concepts so that you know how exactly it is measured. Okay.
SHG consists of platinum wire that is connected to a PT surface in contact with an aqueous solution containing 1 mH plus in equilibrium with H2 gas at a pressure of 1 atmosphere. Let's take a look and see what happens at the standard hydrogen electrode. In this hydrogen electrode, hydrogen gas is bubbled around a platinum electrode. In the molecular view, the PT surface catalyzes the oxidation of hydrogen molecules to protons or the reduction of protons to hydrogen gas. At the electrode, hydrogen gas can either be oxidized to form hydrogen ions, or hydrogen ions can be reduced to form hydrogen gas. Hence, two reactions are possible at the electrode. Oxidation. H2 gives 2H plus 2E minus. Reduction. 2H plus 2E minus gives H2. This reaction is assigned a standard electrode potential E of 0.00 volt and serves as reference. As you remember, two half cells complete a voltaic cell. Let's take a close look. Here on the left, we have zinc half cell, and on the right, we have standard hydrogen electrode. The electrons are moving from zinc electrode to hydrogen electrode, so zinc is being oxidized. The voltmeter shows that the standard cell potential of a galvanic cell consists of a SHE and a Zn by Zn2 plus couple is E cell is equal to 0.76 volt. Because the zinc electrode in this cell dissolves spontaneously to form Zn2 plus aqueous ions, while H plus aqueous ions are reduced to H2 at the platinum surface. The standard electrode potential of Zn2 plus by Zn couple is minus 0.76 volt.
Right? So it was pretty basic. It was already discussed in the sessions. So this was sort of a revision as how we are measuring these standard potentials and how we know that they are the numbers and the values. So this is, for example, this in this question itself they asked about the lithium. So it's good to know that what is the potential of these. It helps in solving the problems, as well as it gives you an idea when you work in the like practical field related to this. If it is a bit difficult, because obviously you cannot learn all of these, and it's like very difficult also sometimes, but just have this idea that what are the standard potentials which are above SHE and what are the potentials which are below SHE. Okay, moving to the next question. What it says Y. Yao and J. T. Kumar studied ionic conductivity in solids and showed that sodium ions can move at the same rate blank. Kumar also proposed the use of this configuration for batteries in a patent from 1969. It's a theoretical question and it was not covered also because it's general information. So I'll give you guys 45 seconds. Yeah, because it's just theoretical. So I just want you guys to at least attempt this question. Okay? Yeah, and your time starts now. Yeah, so let's move on with the question. The answer is solids as in salt melts. Okay, so we'll see what exactly it means. The working principle, so it's just a revision and it will help you in understand that question also. Okay, so the working principle of a battery is relatively straightforward in its basic configuration. The cell is composed of two electrodes, each connected to an electric circuit, separated by an electrolyte that can accommodate charged species. Frequently, the electrodes are physically separated by a barrier material that prevents them from coming into physical contact with one another, which would cause the battery to short circuit. In the discharge mode, when the battery serves to drive the electric current, an oxidation process takes place at the negative electrode, resulting in electrons moving from the electrode through the circuit. A complementary reduction process takes place at the positive electrode, that is cathode, replenished by electrons from the circuit. The cell voltage largely depends on the potential difference of the electrodes, and the overall process is spontaneous. For rechargeable or secondary type of batteries, the process can be reversed and external electricity can be used to produce complementary redox reactions at the electrodes. This process is energy dependent and non-spontaneous. So this is the basic representation of such a battery, that there will be a barrier, there will be electrolyte and an electrode. So from the negative or the anodic part of the cell, the electrons will flow towards the cathodic or the positive electrode of the cell. So this is how the galvanic cell works. Now again we are studying this since the beginning. We'll see one brief info about that, and it's here.
Rechargeable and lightweight, lithium batteries have changed our lives on the way we communicate, move, and work. Let's see how they were born and how they work. These batteries have revolutionized the way of storing energy since the early 90s. The real protagonist is lithium. This metal is the lightest solid element in nature. Pure lithium is unstable, but more common is a positively charged lithium ion, which is formed by the release of an electron. Thanks to the positive charge of this particle, these batteries can be charged over and over without reducing efficiency. To understand how this battery works, first it's important to remember how this great invention was discovered. In the 1970s, as the world was affected by the oil crisis and was looking for alternative sources of energy, Stanley Whittingham was working in the energy field at Exxon and was researching solutions to the problem of energy storage inside rechargeable batteries. The British researcher was immediately struck by the ability of lithium to easily donate electrons, and his studies led him to use metal lithium as the anode of the battery. That is the negative electrode from which electrons move. Instead of the cathode, Whittingham used a metal made of titanium disulfide, a compound that can store lithium ions inside. Whittingham's battery worked like this. The lithium ions and electrons moved from the anode to the cathode with titanium disulfide. Then they were brought back when the battery was charged. The only problem with this battery was the lithium metal used in the anode, which caused explosions. Even if some changes were made, Whittingham's work was discontinued due to the oil price fall. During the 80s, the American chemist John Goodenough realized that by changing the cathode's constitution, it would be possible to increase the power of the batteries by replacing the titanium disulfide with cobalt oxide, and he discovered they generated 4 volts, twice the power of Whittingham's batteries. The need for lighter and more powerful batteries gave necessary impulse to research. Akira Yoshino was considered the third protagonist of the evolution of the lithium battery. He thought he could use petroleum coke for the constitution of the anode material to house the lithium ions, in a similar way to what had been done by cobalt oxide in the cathode. The result was a stable, lightweight, and safe product, ready to become a commercial product. In fact, these advances allowed Sony and Asahi Kasei to start selling these batteries in 1991. As we have previously described, the main feature of a lithium-ion battery is the composition of its anode and cathode. There are many types of lithium-ion batteries, each with different characteristics and applications. For example, cobalt oxide lithium batteries are specific for smartphones and laptops. They are formed by a cobalt oxide cathode and a graphite anode. In the automotive sector, on the other hand, the batteries of electric vehicles have a particular chemical composition: lithium, nickel, manganese, and cobalt. With this composition, the battery charge is optimized and maximum energy is provided. Furthermore, thanks to the nickel, the battery obtains a high specific energy, while the manganese microcrystals form a three-dimensional structure that favors the flow of electrons, reducing the electrical resistance and allowing a control of the current. This is because electrons pass through microscopic channels. This structure, in fact, looks like a grid of crystals. This type of battery can have different cathode combinations: 1-1-1, wherein a part of nickel, a part of manganese, and a part of cobalt are present, or 5-3-2. Because of the high cost of cobalt, battery manufacturers are trying to replace it in favor of nickel.
So this was a little bit too much information with respect to batteries, but yeah, it's never bad to know all the details, correct? moving towards our next question. So what our question says, it says read the following statements and then see which statement is true or false. Okay, so our first statement says the activity of an ion in a very dilute solution is close to infinity and can therefore be expressed in terms of the ionic concentration. However, the ion concentration is not equal to the ion activity for solutions having very high concentrations. To use the Nernst equation in such cases, experimental measurements must be conducted to obtain the true activity of the ions. So these are the statements and we need to tell which option is correct. So the first option says 1 and 2 are true while 3 is false. All three statements are true, that is 1, 2 and 3. Statement 2 and 3 are true while statement 1 is false, or all of the statements are false. I'll give you guys 1 minute to solve this problem and please write your answers in the chat box. Yeah, thank you, and your time starts now. I think we can move ahead with the answer, and the answer is that all three equations are correct, because the how we actually use Nernst equation, these are the assumptions that we use while using the Nernst equation, and hence the SHE is always 0 if it is iron. If it is pure material, then it, if you go through the lectures, which I suggest you that you should, you will understand why these statements are assumed when we have to consider the elements which are there for the battery purposes, for using in the battery and calculating the reduction potentials of the battery. So this is the brief about the Nernst equation. Okay, this is very useful equation to know.
Well, the Nernst equation is really a story about two opposing forces, the electrical potential versus the chemical potential. Let's use the classic example of a ball on top of a hill to illustrate our point. Now, when the ball is at the top of the hill, it has stored energy, otherwise known as potential energy. Potential energy is equal to the height of the ball times the mass of the ball times the gravitational constant. If we let the ball roll down the hill and quickly apply an opposing force to stop the ball, that opposing force, or kinetic energy, must equal the potential energy in order to stop the ball. The Nernst equation describes a very similar process for the movement of charged particles like sodium, potassium, or chloride ions across a cell membrane. Like the ball on the hill that wants to roll down, molecules want to move from high concentration to low concentration. In other words, they want to move down their concentration gradient. The size of the concentration gradient can be quantified using the chemical potential equation. Now, if we want to prevent the charged molecule from moving down its concentration gradient, we must apply an opposing force. In this case, that opposing force is referred to as the electrical potential. Now, if we apply a sufficient electrical potential so there is no net movement of the charged molecule in or out of the cell, we will have reached the equilibrium potential. And that's exactly what the Nernst equation describes. In other words, the electrical potential represents the potential in millivolts, where there is no net movement of charged molecules in or out of a cell for a given chemical potential or concentration gradient. So now that we have a general sense of what the Nernst equation represents, let's describe the Nernst equation in greater detail. Now, the Nernst equation is typically denoted as such, where E represents the electrical potential given in millivolts, and X represents the identity of the charged molecule. R represents the gas constant, which equals 8.31 joules per Kelvin per mole. T represents the temperature in Kelvin, which equals 298 Kelvin at 25 degrees Celsius. Z represents the valence of the charged particle. For example, sodium and potassium ions carry a valence of +1, chloride and bicarbonate ions a valence of -1, and calcium ions a valence of +2. F represents the Faraday's constant, which equals 96,500 coulombs per mole. And finally, Ln represents the natural logarithm of x in over x out, where x represents the intracellular concentration of the charged particle, while x out represents the extracellular concentration of the charged particle. Both are given in moles. Now there's a much easier way to remember the Nernst equation. I'll show you by simplifying it. First, we'll cancel out like terms. The Kelvin units in the gas constant and temperature can cancel each other, as do the mole units in the gas constant and the Faraday's constant. Next, let's convert joules to coulombs times volts, or V. And with that, we can cancel out the coulomb units in the gas constant and Faraday's constant, leaving us with volts. Now, if we solve for RT over F, we get 0.02567 volts, or 25.7 millivolts at 25 degrees Celsius, or 298 Kelvin. Next, let's change the natural logarithm to log base 10 by multiplying everything by -2.303, which yields negative 59.2 millivolts over Z. Now, let's say the intracellular concentration of the charged particle equals 10 millimoles, and the extracellular concentration equals 100 millimoles. Now, the log base 10 of 10 millimole over 100 millimole equals -1. So minus 59.2 millivolts over a Z of +1 times -1 gives us an equilibrium potential of positive 59.2 millivolts.
Right? So it was pretty easy to understand, right? So this is how you can derive the Nernst equation, and you know what are the individual components involved in the Nernst equation and how you can get them at the end of the day to help you calculate the standard potential for your own system. Okay, let's move to our next question. So our next question says, lithium based batteries initially used blank as the anode, blank as the cathode, and lithium perchlorate in dioxolane as the solvent, but because the perchlorate proved unstable, it was later replaced by tetramethyl borate despite a less optimal lithium plating with this electrolyte. So if you're seeing the videos carefully, you will be able to answer this. You guys have 1 minute for this particular question, and your time starts now. copper? So the right answer is lithium and titanium S2. You see now that it was exploding the batteries, hence it was later replaced with less optimal electrolyte. Okay, coming to the next question. This question says enthalpy, the blank of the internal energy and the blank of the pressure and volume of a thermodynamic system. So you need to know what is enthalpy exactly. Okay, enthalpy, I'll just give you guys a hint, it is the total internal energy. Okay, so I'll give you guys 1 minute for this, and hopefully I can see some answers in the chat box. Your time starts now. Your time is up, and the right answer is sum and the product. So enthalpy is the sum of the internal energy and the product of pressure and volume of a thermodynamic system. So enthalpy, again, this is the definition of enthalpy, that it is the sum of thermodynamic systems internal energy and the product of its pressure and volume. This is how the enthalpy is represented. It is like H is equals to U plus PV, meaning the system which we are taking as an ideal gas. So when we supply the heat from the outside to this system, this will increase the internal energy and it will expand, which means the gas expands due to the pressure and it will increase in the volume. So the work is done by the system on the surrounding. Hence enthalpy is equals to internal energy plus pressure into volume. Okay, because this is the total energy of the system. Moving to the next question, it says multiplying a half reaction by any number does not change the value of. So what this is asking, it is asking which one of the following is a property if we multiply it by any number, whatever the magnitude is, its value won't change. So think about it. You guys have 1 minute for this particular question and your time starts now. So the out of these, enthalpy, entropy, bond energy and standard reduction potential, standard reduction potential is the one which is an intensive property. Okay, so what exactly is a intensive property? Since the number of electrons lost must equal the number gained, the half reactions must be multiplied by integers as necessary to achieve the balanced equation. However, the value of electron is not changed, reduction potential is not changed when a half reaction is multiplied by an integer. Since a standard reduction potential is an intensive property, it does not depend on how many times the reaction occurs. The potential is not multiplied by the integer required to balance the cell reaction. So what exactly we mean by extensive and intensive properties? So extensive properties like mass or energy depends upon the amount of the substance. If you double the reaction, the number of electrons transferred increases. Okay, if you put more mass, it will be having more atoms, it will transfer more electrons. So it's an extensive property. Intensive properties like voltage or temperature do not depend on the amount. The potential stays the same no matter how many times the reaction happens, which means, for example, if you have taken lithium, if you take any amount of lithium, its potential won't change. Its potential will be minus 3.05 irrespective of how much you are taking. So a standard reduction potential is an intensive property. Okay, moving to the next question, we have, when a nerve cell is at rest, blank and blank cannot pass across the membrane of the axon, but blank can flow across the membrane from the cell's interior to the exterior. As a result, a blank potentials exist across the axon membrane. So if you remember the action potential video and the things which we have discussed before the beginning of this lecture, you will be able to answer this. I'll give you guys 1 minute to solve this question and time starts now. I hope you guys are able to answer this. So the answer is, when a nerve cell is at rest, sodium ions and chloride ions cannot pass across the membrane of the axon, but potassium ions can flow across the membrane from the cell's interior to the exterior. As a result, a negative potential exists across the axon membrane. Okay, to revisit our concepts of this nerve cell potential and the action potential, let's have a brief about it. Okay.
In the last 20 years, CGM
This is a neuron, which has four main parts. The dendrites receive information. The cell body processes and integrates that information. The axon carries the information along long distances from one part of the neuron to another, and the axon terminal transmits the information to the next cell in the chain. A bundle of axons traveling together is called a nerve. Nerves can be very long as they often need to transmit information over long distances. As we just saw, the dendrites are the part of the neuron that receives incoming signals. Based on the strength of this incoming stimulation, the neuron must decide whether to pass that signal along or not. If the stimulation is strong enough, the signal is transmitted along the entire length of the axon in a phenomenon called an action potential. When this happens, we say the neuron fires. Transmission of a neuronal signal is entirely dependent on the movement of ions or charged particles. Various ions, including sodium, potassium, and chloride, are unequally distributed between the inside and the outside of the cell. The presence and movement of these ions is not only important when a neuron fires, but also at rest. To start, let's think about the positively charged sodium and potassium ions. When a neuron is not sending a signal, it is considered to be at rest. In a typical neuron, in its resting state, the concentration of sodium ions is higher outside the cell than inside. The relative concentration of potassium ions is the opposite, with more ions inside the cell than outside. This ionic separation occurs right at the cell membrane and creates a chemical gradient across the membrane. Because ions are charged particles, we also need to consider their charge when thinking about their distribution across the membrane. At rest, there are more positively charged ions outside the cell relative to the inside. This creates a difference in charge across the membrane, which is called an electrical gradient. Together with the chemical gradient we already mentioned, we refer to this ionic imbalance as the electrochemical gradient. The difference in total charge inside and outside of the cell is called the membrane potential. At rest, when no signals are being transmitted, a neuronal membrane has a resting potential of approximately -70 millivolts. This means that the inside of the cell is approximately 70 millivolts less positive than the outside. Both the chemical and electrical gradients we just discussed contribute to establishing this potential. While the inside of the cell has a net negative charge and the outside of the cell has a net positive charge, the charges line up at the membrane and the bulk solution on either side is actually electrically neutral. The resting membrane potential is the point where the cell has achieved electrochemical equilibrium. This means that the concentration gradient and the electro gradient for each ion is equal and opposite. Ions cannot simply move across the membrane at will. Instead, they need a protein embedded in the membrane to facilitate their movement. Most ions cross the membrane through a structure called an ion channel. Ions move through channels by passive diffusion along their concentration gradient. Some ion channels are always open, but many require a signal to tell them to open or close. For example, voltage-gated channels only open when the membrane potential reaches a certain value. On the other hand, ligand-gated ion channels are triggered to open when they are bound by a specific molecule. Mechanically gated ion channels open in response to physical forces such as changes in length or changes in pressure. Most ion channels are selectively permeable, meaning that they only allow one or a small subset of ions to pass through. Voltage-gated ion channels, for example, typically only allow a single ion to cross the membrane when they open. This means that we need separate channels for each ion, i.e., voltage-gated sodium channels as well as voltage-gated potassium channels. As ions move through a channel and cross from one side of the cell membrane to the other, they cause the membrane potential of the cell to move away from its resting potential. If the resulting change in membrane potential is small, we call this a graded potential. Graded potentials can vary in size, can be either positive or negative, are transient, and typically do not result from the opening of voltage-gated ion channels. When ion channels open and a graded potential occurs, the neuron moves quickly to reset its membrane potential to resting values. This is accomplished primarily by the use of the sodium-potassium pump, which uses the energy generated by ATP hydrolysis to actively transport ions across the membrane against their concentration gradient. In other words, sodium is transported to the outside of the cell, where its concentration is higher, and potassium is transported back into the cell, where its concentration is higher. One cycle of this pump transports 3 sodium ions outside the cell and brings 2 potassium ions inside the cell. This unbalanced charge transfer contributes to the separation of charge across the membrane and also to the ionic concentrations we see at rest, thus restoring the chemical and electrical gradients to their resting levels. Maintaining these ionic balance in neurons is so important that this process can account for 20 to 40% of the brain's total energy use. Only when the resting membrane potential and ion distributions are maintained at precise levels will the neuron be poised and ready to fire an action potential. When the outside stimulation is large enough to bring the membrane potential in the neuron body up,
the repetitive things which we have seen. It's there in the slide. You guys can check it out. And if you have any doubts or problems, feel free to contact me. Okay. So I've added these resources so that whenever you guys find it difficult, you can always go back to the main lecture. So our next question says the concentration of potassium ions inside human nerve cell is typically, again this is a theoretical question, I'm going to give you guys 40 seconds for this, because if you know, we have discussed these concentrations just prior to jumping into our questions. So if you remember that, please feel free to drop your answer in the chat box, and the time starts now. So the correct answer is 150 millimolar. Sorry, yeah, 150 mole. So the inside potassium is more in comparison to the outside potassium. Okay. Last, I guess, So maybe this is the last question for today. So in early glucose sensors, hydrogen peroxide was measured. The blank was proportional to the concentration of hydrogen peroxide, which in turn is proportional to the glucose concentration in blood. So if you know about glucose monitors, you'll be knowing that it works on the principle of by using the basic principles of bioelectrochemistry at the end of the day. Okay, so I'll give you guys 30 seconds to attempt this, because I don't think so that you guys might be aware of it. But if you are, please feel free to answer in the chat box. Otherwise, we gonna see a relatable basic information video with respect to the continuous glucose monitors. And time starts now. current. Now we'll see what it means. So there are different type of sensors which work to basically on the biological system based upon the principles which we are studying right now, to work as a detector or to work as a sensor or to work basically as a data collecting system. Okay, so this is one of the main device which we use to make sure that we can measure our glucose concentration in the blood. This is especially for the diabetic patients, so that they can either take their medicine on time, adjust their diet, and all those things can be done if they know what is the level of their glucose. So how exactly we are measuring that, we'll see it now.
In the last 20 years, CGM has transformed the way diabetes is managed. The evolution of glucose monitoring was transformed with the introduction of CGM, continuous glucose monitoring. At Dexcom, the first real-time CGM for patients was introduced in 2006 with the so-called STS, short-term sensor. This technology allows people with diabetes and healthcare professionals to monitor glucose readings on a receiving device or app, allowing analysis and the possibility of more accurate treatment decisions. A RT-CGM system may reduce the need for a person with diabetes to finger prick on a regular basis, or in the case of Dexcom, reduce it to 0 when general requirements are met. The body is steadily releasing glucose into the bloodstream, which then moves into the interstitial fluid surrounding the body's cells before being absorbed by the cells for energy. When taking a reading from a finger prick, you are measuring the concentration of glucose in the blood, which is referred to as a blood glucose reading, whereas a CGM sensor is inserted on the back of the upper arm, abdomen, and for children 2 years until 17 years, also on the upper buttock, and measures the amount of glucose in the interstitial fluid, which is referred to as a sensor glucose reading. It's important for people with diabetes to understand that these two readings will rarely be exactly the same, as the glucose within the body is constantly moving. The Dexcom RT-CGM system consists of 4 parts. 1. A small sensor that measures glucose levels just underneath the skin. 2. A transmitter that fits onto the sensor and sends data wirelessly to the receiver or compatible smart device. 3. A small receiver or compatible smart device that displays real-time glucose information. 4. Software for data interpretation, providing continuous detailed analysis and automatically generated patterns. The Dexcom G6 and G7 RT-CGM system can provide up to 288 real-time readings in a 24-hour period, giving valuable insight into glucose levels, whether they are high or low, stable, rising or falling, and what happens while you sleep, eat, exercise or are unwell, all enabling proactive management of diabetes. With Dexcom G6, alerts for rising or falling levels help manage diabetes both when awake and asleep. Clinical studies have shown that Dexcom RT-CGM use is proven to both reduce HbA1c and time spent in hypoglycemia among people with type 1 diabetes, regardless of their insulin delivery method. Dexcom RT-CGM use is also associated with an increase of time spent in range and a significant reduction of severe hypoglycemia and hypoglycemia at night. Within a number of rigorous studies, Dexcom's performance has shown excellent results, including accurate reading of levels on day 1 of sensor insertion, consistent accuracy of readings over time, accuracy of readings across different glucose ranges. 84% of participants reported no pain or only mild pain when inserting a sensor. 100% of participants reported the auto-applicator was somewhat or very easy to use. This, paired with the alerts and alarms available, makes Dexcom a leading option for diabetes treatment. In people without diabetes, the glucose level in the blood stimulates insulin production in the pancreas. Insulin and glucagon, both hormones, are produced in the pancreas and are responsible for the balance of the glucose levels. In people with type 1 diabetes, this process has to be imitated. This generally requires the use of an insulin pen or pump and a blood glucose meter or CGM device for monitoring glucose levels. The individual then calculates the insulin required and delivers it through the chosen method. In the future, the diabetes community would like to see a closed-loop system where the calculation and delivery of insulin will become automatic using an algorithm, RT-CGM, and pump. The Dexcom G6 RT-CGM system meets the rigorous performance requirements of the newly established Class II iCGM device category by the FDA. It's important to understand that this classification is not to be confused with the classification of medical devices under the EU directive. The new iCGM category stands for Interoperable CGM. This means that in addition to our collaboration with the Tandem insulin pump, Dexcom sensors may potentially in the future have the capabilities to be combined with other insulin pumps, automated insulin delivery, and smart pen systems, as well as dedicated algorithms, opening up new possibilities for therapy and dosage. At Dexcom, we are passionate about progression of technology and empowering people with diabetes to manage the disease.
Okay, this was just one company's basic information about the continuous glucose monitoring. Okay, I'm sorry for that. Yeah. Moving to our last question for today. So, ferrocene contains flat blank membered ring similar to benzene. So it's just a information based question. The answer is 5, and ferrocene is an organometallic compound with the formula of FeC5H52. The molecule is a complex consisting of two cyclopentadienyl rings sandwiching a central iron atom. It is an orange solid with a camphor-like odor that sublimes above room temperature and is soluble in most organic solvents. So this is how it looks. It's a little bit different kind of structures which you guys might have seen till now. Okay, so this is all from my side with respect to today's session. I hope this is fine, and see you in the next session. The next session will be on Tuesday instead of Saturday. Okay, so thank you for joining in.